Swayam Prabha. Digital India. Educated India.
Hello, welcome again to our this video lecture on basic surveying. Today we are in module 2 and lecture number 4, and the name of the module is Basic Concepts of Surveying. Well, in the entire structure of our this video lecture, we are here at the moment in the module number 2. What we have done so far, we have discussed lecture number 1, 2 and 3, and there in the 3 we talked about various things, particularly about the errors in the measurement, because surveying, as we said, is about measurement, and whenever we are taking a measurement, we are introducing, there is some error coming into the observation. So we need to understand about those errors. What are their sources? This is what we discussed. We saw the sources could be natural, could be the human induced, the personal ones. Also, the instrument which you are using may result in some kind of error. We saw some examples also of that. Then in the classification of errors, the errors could be, the blunders which we commit. We saw it, instead of writing maybe let us say 31.5, what I am writing 3.15. So things like this may happen, and these are the blunders, mistakes. Then the second one, there are various physical forces which are acting. The temperature is maybe more, the gravity is working, the wind is blowing, and many of these factors, they contribute some error again in the observation. But about these errors, we can quantify them. We can write a mathematical model, we can write, because we know the physical law behind these errors. So from our observation, we can eliminate those errors. So these errors which can be eliminated by writing a mathematical law are called systematic errors. Then next we discussed was about the random errors. From your observation sets, you have eliminated mistakes or blunders, taken away them. You have also taken away the systematic error component. Still your observations are not true value. We saw that it is never possible to observe the true value. So what we saw at this stage, the errors which are there in the observations are random errors. We saw the distribution. What kind of distribution is there for the random errors? They are equally in positive and negative side. Small errors, okay, the small errors have got high probability, while the large errors on the side of the curve, we saw it had less probability. Then we talked about principle of adjustment. When the errors are there in the observation, many times, our network there in the field, for example, we had an example of the triangle. So the geometry from the field says the sum of those three angles in a triangle which we have measured should be 180, but we saw it is not so, because in each and every theta which we measured the angle, we had some error. So we need to adjust our observations so that they conform to the geometry which is there in the field. Well, we didn't talk about this principle of reversal. We will talk about this principle of reversal later on when we are talking about some instruments, adjustment of the instruments. Then we saw some more basic terms, the true error, okay, the percentage error, relative error. One very important concept we looked at was the most probable value. Most probable value is a value which has maximum chances of being nearest to the true value. Then we saw how we can find it. We proved it that the most probable value for a set of observations is the arithmetic mean. Well, towards the end of the lecture, we were looking at the random error distribution, and we saw that the random errors are normally distributed. We saw that bell type curve. So what we will do today, in our today's lecture, we will again look into a little detail of random error distribution, while mostly we will be talking about use of normal distribution curve, because we know our errors follow this pattern. We can assume it very safely. So, we will try to make use of this normal distribution curve. We will have some indices for the precision. Also, we will go for the weighted observations. What are the weighted observations and their measures of precision? Then we will try to see, if the time permits in this lecture, that how we can detect the outliers and what happens in case of the error propagation. So, this is all we are going to talk today. So, now what we will do, we will look a little bit, of course we have seen it before also, into the normal curve. The normal curve, as we saw yesterday or maybe in the last lecture, was like this. Any variable x, okay, may have an arithmetic mean which we can determine, and the probability of occurrence of this x is y. So, this y is written as f x, which is given by 1 by sigma 2 pi. You can determine this sigma, standard deviation, we saw the formula for that, raised to power half x bar minus x upon sigma square. Okay. Our observations in surveying, our errors, the random errors, and this is true only if from our observations the blunders, mistakes have been taken away. Those observations which were blunders or mistakes, they have been taken away, and also from our observations the systematic error has also been taken away. Then only, if only random errors are there, then we can safely assume that our observations will follow this pattern or this curve. Now, what we will do, we will try to see how we can make use of this. Before that, what we will discuss, standard normal curve or standard normal distribution. Now, what is this? Generally, a normal distribution is written as mu sigma square. The meaning is the distribution for a variable, let us say x, is normal, and the normal distribution is given by two parameters, the mean, which is the most probable value, and the standard deviation. So, these two, they define the normal distribution curve. For a standard normal distribution, we write it as 0 and 1 square. So, you can understand, for a standard normal curve, if the variable is z, the mean of the variable is 0 and the standard deviation is 1. Well, I can plot it also. If you plot it like this, the meaning is this value is 0, while the standard deviation, we will see in a while, is -1 and +1 here. We will see this sigma term, how they are coming here, what this point is. We will look into this in a while. So, for a standard normal curve, what we can do slightly more. We can write it as f z, as in the previous case, the equation of that, 1 by sigma is 1 and root 2 pi e raised to power minus z square by 2, because in this case the mean is 0. So, it reduces to this. What we will do, we will try to make use of this standard normal curve, because for standard normal curve we can compute the probability of occurrence of these values here. There are some standard tables. We will try to make use of those tables in our computations. So, this is why we need to discuss this. Now, before that, what I will do, I will write a term here For example, let us say there is a variable x for which the mean is x bar and the standard deviation is sigma. So, we can write this normal distribution as x bar and sigma square, and this we can show like this, where this x may vary from minus infinite to plus infinite. Now, I write a term here, I write that probability that my variable x is less than equal to a value x. What is the meaning of this? I am looking if this small x, this value is somewhere here. What I am looking at? I am looking at now by writing this, what is the probability of occurrence of my variable x so that it is smaller than the value x. Now, as you know, in this curve, at any point here, this is the probability of occurrence of this particular value. What we are looking here for? We are looking here for all the values which are less than and equal to x. So, what is that probability? That probability is basically the area of the curve here. So, this area we can also find as, I can write it as, let us say, f small x is integration of this curve from minus infinity to x, f x is my this curve into dx. So, what it will do? It will give me the area of the curve in between these two. Now, let us look at this thing slightly different way. What is this really? This is telling me the cumulative probability, the probability of occurrence of all the variables, all the values from minus infinite to x is this value. So, this is actually the sum of all these probabilities starting from here to there, starting from minus infinite to here at x, because we are taking this area. So, we say this as cumulative probability distribution or density function, because this is the probability density function, and this is now if f x is being plotted with x, that will become cumulative probability density function. Many times this is also called as simply distribution function. Distribution function, this f x. Now, we will try to plot these two together. Okay, I am plotting my normal curve first. Here is the normal curve from minus infinite to plus infinite for my variable x. This is the probability of occurrence of any value here. Now, what I am doing? I am plotting along with this in the same line here my another curve, and this curve is for f x. For against the value is x. Well, what we had done in our last slide, we had computed the value of f x at x, this is small x, and that was this area, and the value was f x, which we said the cumulative probability density function or cumulative probability density or cumulative probability as such we can say. Well, if I plot this x against this x here, what we will get? We will get a curve like this. Now, you can very well tell me, you can guess it now, that what will be the value of this total one. what this total 1 is? This total 1 should be 1. Why? Because the probability of occurrence of all the variables, all the values starting from minus infinite to plus infinite, all of them, they will occur. What is the probability of that? The probability is 1. So, the cumulative probability will be 1, while at this place this particular value is f small x at a small x, and this value will be 1 minus f x. Okay. So, for our standard normal curve, what we are looking at, and standard normal curve 0, 1 square, these values are known. There are some standard tables where all these values are known against the variable. So, we will make use of those in a while. Well, in order to make use of that, I am writing here now again for a variable, let us say it is capital X, and its distribution is normal distribution. The meaning is, from our observations, all the systematic and blunders, they have been taken away. Only we have got random errors. This is why this distribution will be there. Well, what I try to find? I try to find now between two values, x1 and x2. So, these are two realizations, x1 and x2, of my random variable x. Okay. I am trying to find the probability that my variable is between x1 and x2. Now, what is the meaning of this first? Let's understand the meaning. The meaning of this is, what is the probability of occurrence of all the values which are between x1 and x2, and this, as you can see here, is actually this area. So, we need to integrate our curve starting from this point to this point, and to do that we should know the characteristic of the curve. Now, what we will do, we will make use of standard normal curve in order to find this value. Now, to do that, what we do, we find, as we had written earlier also, z. Z is the normalized variable. What we are doing, we are transforming this variable x here, and this transformation is x minus the variable x bar. X bar is the mean of this variable divided by sigma, the standard deviation of this variable. So, using this, we can transform our variable capital X here into the standard variable, or into the standard normal curve variable. Now, this particular variable z has the normal distribution, which is 0 and 1 square. Okay, why we did it? What is the use of this? To see the use of this, the probability that x, capital X, is between x1 and x2, the probability of occurrence of capital X between these two variables is actually same as the probability that my normal standard variable occurs between z1 and z2. Now, what these z1 and z2 are? Obviously, you can find z1, again the transform variable, and the z1 will be the transform variable 1 by minus x bar sigma, and similarly your z2 x2 minus x bar by sigma. So, you can transform your values now, the value x1 and x2 into z1 and z2. Okay. So, if we have done so, we would like to determine the value of this, because we are saying that it is possible to find this value from the standard normal curve tables. How to find this value? This value we can write further, and to explain that I am drawing again my standard normal curve here. This is for my z where it is 0. Let us say the z1 and z2 are here. This is my z1 and this is my z2 corresponding to my x1 and x2. Basically what I am interested in? I am interested in this area. The moment I write this is actually the area here, the shaded area, shaded part. How can I determine this shaded part? To determine this shaded part, well, let us say if I can determine this entire part which has the dots, what this will be? The one which has the dots will be probability that my z is less than equal to z2, isn't it? Then if I can also determine the area here, if I am drawing by these lines, can I determine these ones? Let us say the area, this one is probability that my z is less than equal to z1. Now, having known this and this, if I can differentiate, you can find the difference of these two. So, this total area minus this area here will give me the area under the curve here. So, by determining this and this, I should be able to find this probability. Well, these are the values which you can get from standard normal curve or from standard normal curve tables for any value of standard variable. Now, this is standard variable. These are the standard tables of z1 and z2. You can find these two values, you can find their differences, and by finding that, in fact, what you are finding, you are determining the probability of occurrence of x in between x1 and x2. What we will do, we will make use of this now. How it is useful to us, why we are talking about it. So, we will make use of this. Well, to make use of this, what I will do, I will draw again the normal curve for a variable x, and of course, this is the mean, and we also know for this x the corresponding sigma. Then we can say this is normally distributed with a mean of x bar and sigma square. Actually, this is the conventional way, the standard way in which the normal distribution is represented by these two parameters. That is why I am writing it every time. Then a normal curve, the bell shaped curve which we say from minus infinite to plus infinite. Now, we want to make use of what we saw just in the previous slide. We want to make use of the idea is, can we really find what is the probability of occurrence using the normal curve between two values? Now, here in this curve, this point and this point are the point of inflection. Point of inflection, and these points, they are corresponding to the values of sigma, sigma on this side and sigma on this side. Well, can I really find the area of the curve which is within the x bar plus minus sigma? What is the meaning of this? The meaning is x bar minus sigma on this side plus sigma on this side. So, this area which is shaded by red color here. So, what we can do, we can make use of the standard normal curve, and again we can find this area, and this area comes out to be 68.3%. If we are considering the entire area within the normal curve to be 100, then it is 68.3. Similarly, we can also get the area corresponding to plus minus 2 sigma. because our 2 sigma will be here somewhere, and that comes out to be 95.5. We can also find this area corresponding to 3 sigma, which is 99.7. For plus minus 3.29 sigma, the area is 99.9. What is the meaning of these things? What I am writing, why we need it, how we can make use of this? We should see this thing now. To see this thing, what I will do, I will give you one little example here. Let us say we have a length. Okay, the true value of the length is L. We do not know this. We cannot measure it. It is not possible us to measure this. What we do in term, we take several observations of this length L. For example, let us say L1, L2, L3 and so on up to Ln. We take many observations. From these observations, I can find L bar, the mean of these, and as well as I can find the sigma, the standard deviation. You know how to compute the standard deviation. So, once we know these two, also the important point, also we are assuming here while I am saying these observations, the meaning is from these observations the outliers or the mistakes have been taken away. Also, it means from these observations, if at all there was some error component, systematic error component, it has been also taken away. So, these observations have got only and only random error within them. Now, in that case, because our assumption is if only random error is there, then our observations will follow the normal curve, the normal distribution. Well, after finding this sigma and the mean, how to report this observation? Reporting the observation. How do we write it? What do we say about it? Something which we have found, how we present it? Well, I say L bar plus minus sigma is my value. What does it convey? If you measure this length here, after measuring this length, you find the mean of that, you find the sigma of the observations, the standard deviation, and you say, well, this is my mean, this is my standard deviation. What is the meaning of this? What, someone, a third person, what should he understand out of this? What you as an observer, you as an surveyor should understand out of this? The meaning is, because we knew already that in 68.3% or 68.3 was the area within the curve in standard, in our normal curve, which was falling within plus minus sigma. What is the meaning now? The meaning is, we are sure now, we are sure that out of 100 observations, if we take 68.3 observations will be within this limit. This is what the normal curve says. The normal curve gives you the probability of occurrence of any observation, and we have seen that within plus minus sigma from the mean, the probability of occurrence of all the observations in that is 68.3%, that we have seen. So, if I am reporting my measurement like this, so the meaning is, if I am taking 1000 observations, then if the observations have got only the random error, 683 observations out of 1000 will be within plus minus 1 sigma of that. So, it gives you a kind of confidence about your values. For example, let us say I can say at 95.5% confidence, this is a confidence level now. At this level, I can say that my observation is L bar plus minus 2 sigma. What is the meaning? So many times you are sure. For example, if you are taking a little set, For a population, L bar and sigma are the values which you know. Okay, the population is defined, or the normal distribution curve of the population is defined by these two. Then if you take a little set from that population, the mean of that set, of that sample, will have in 95.5% times it will be within this, while this is for the population. So for any set you take, this tells you about your confidence about your observations, and this is how we report our observations. So mostly you will find any instrument. If there is an instrument, you are going to buy an instrument. For the instrument, let us say a simple scale. Well, what is the accuracy by which the scale can measure? So the manufacturers, they will say the accuracy of my scale is, for example, anything. They say plus minus 15 centimeter. You have got some instrument which can measure the length, and the instrument says the accuracy of measurement is plus minus 15 centimeter. You should ask at that time, what is this 15 centimeter? Is this 1 sigma, 2 sigma, 3 sigma, or at what sigma? This is important, because depending this, you will come to know what kind of instrument is that, how good it is for your purpose. At what, because if this accuracy is given at 3 sigma, also in the second instrument it is given at 1 sigma. There are two instruments, instrument A, or a manufacturer A and manufacturer B. They are building the same kind of instrument. The manufacturer A, he says that his instrument can give at 1 sigma this accuracy, while he is saying that at 3 sigma he can give the same accuracy. What is the meaning? Which one is more accurate? You will go for one instrument in which case this accuracy is available in more number of observations, which is here. So we should understand how we are making use of this standard or normal curve. Our concept, our observations are, normally distributed, our errors are random errors. So we should know all these things, and then only we can start making the judgments about the observations, which are reported, because this particular observation or this particular error is reported. So we can start making use of this. So this is important. Now what we will do, we will continue our discussion in the same line. We saw in our last video lecture a term called precision. Okay. Now we have seen so far that what is the meaning of the precision, and I gave you one example where you are firing bullets in the bull's eye. What you are doing in that case, let us say there is a fireman and he is very good. He fires all his bullets very closely here. His observations are, or his firing is not accurate, obviously, because it is away from the bull's eye. But why is it happening? It is happening because of some forces which are working there, some systematic error. And because of those systematic errors, all the observations are clubbed here. Well, there is another person. He is not a very good fireman, and he also fires. Let us say in his case, all his observations, all his bullets are this way. He is also not accurate, because he is also away from the bull's eye. Again, in his case, some systematic error is taking place. But if you look at these two, you will appreciate this person A for his very, very precise firing than the person B. Just by looking at this diagram, you are able to say, well, the person A is a better fireman than the person B. Now how? What made you think that? Because somewhere you are talking of precision. That precision over here in these bullets is shown by the spread. Spread of bullets. are they spread widely or in a very narrow area? So, this spread is an indicator of the precision. Now, what we do? We will try to take the same concept into the surveying observations. Let us say there is a length, L is the true length, which we do not know. There are two observers, A and B. Both of them, they measure this length. A also comes here and he takes several observations. For example, he takes L1, L2, L3 up to Ln. And the B also takes several observations. For example, let us say L1, L2, I am writing them by red in order to differentiate, L3, Ln, or let us say Lm, different number of observations, whatever. Now, just by looking at these observations, can you speak about the precision? Who is more precise out of these two? Well, what we do in this case, we will make use of again our normal curve. As in this case, even if you eliminate the systematic error from your observations, all your observations will shift here and they will still form a closed group. Here also, if you eliminate the systematic errors, all your observations will shift somewhere here and again they will form a widely spread group. Okay. So, what we are doing? Maybe from these observations also we have taken away the systematic error component. It has been taken away. So, in your observations only the random error is there now, and this is why I am saying that now henceforth, because it is only random error, we can make use of the normal curve. So, we will make use of the normal curve. Well, for this first set of observations, I find the L bar and the sigma. Let us say I should write it as sigma A. For this set of observation B, from the B I find again L bar and I find sigma B. You can compute these. Of course, we are assuming in our observations there is no systematic error component, there is no outlier or there is no any mistake or blunder. Well, how to make use of these two in order to see which observation is more precise? What I will do, I will try to plot it now. The plot of these observations may look like for B, let us say for the B, the plot looks like this, and for A, the plot looks like, it's quite possible. Now, what is the meaning of this? The meaning of this is for B, the standard deviation will be, the point of inflection is somewhere here, and that is the value of the standard deviation, which we have already computed. So, this total is 2 sigma B. We have already computed sigma B from the observations. For observer A, the point of inflection should be somewhere here, and we have already computed sigma A. So, this is 2 sigma A. Now, look at these two curves. Do they say anything about precision? Are they any kind of indicator of the precision? Just look at that. What we saw earlier, we said within plus minus sigma, there are 68.3% observations. So, now we are trying to relate these two curves with the precision. This statistics, we are talking that within plus minus sigma 68.3% points or observations will be within plus minus sigma. What is the meaning of that? The meaning is here in this case the deviation of the observations from the mean, how many observations? 68.3% observations is only within this limit. So, the deviation is less. The meaning is observations are closer, they are nearer to each other. While in the case of B, the deviation of the observations from the mean, because that is our sigma, 68.3% observations are spread in this area, in a wider area. So, the deviation of the observations from the mean is more here. So, this is something like a big spread, while this particular one is like a small spread. So, what we are doing? We are relating our standard deviation with the precision. So, standard deviation is an indicator of the precision. If you can find the standard deviation, so here in this case the standard deviation of A is smaller than standard deviation of B. So, we can say these observations, the A observations are more precise than the observations B, which is very much obvious from here. Now, there is one question. The question is, for example, here only in this slide, both of them they find for this length some mean value. Let us say I am writing this mean value here as LA and LB. Both of them they have found some standard deviation also, and by the way, incidentally this standard deviation are equal. Now, what we end up with? Two observers, they went to the field, they measured one length. One has done the observations n number of times, the other has done the observations m number of times, and both of them they come to the laboratory, they present their results. They have one mean, one standard deviation, another mean, another standard deviation. Incidentally, both these standard deviations are same. Now, out of these two means, which one is a better estimate of this length? The standard deviations are coming to be same. Can we say that the mean which is found from these observations is equally precise? Are the means same? Are the means with same confidence? Can we say so? The one thing which is different here, that is about number of observations. If you are taking only 10 observations in this n, and we are coming with these two. In another case, let us say in case of B, we are taking 100 observations and we are coming again with this. Are these two means equally confident? Can we be equally confident about these two means? So, in order to solve this problem, because this really leads to a kind of confusion, there is a term which is called standard error. What we do? We find the standard error as the standard deviation divided by under root of number of observations. What we have done now in this case? If let us say for the length which we measured it n1 times and n2 times, while n1 is more than n2, and in both the cases, for case A, case B, we had the same sigma. So, what we get? We get sigma by under root of n1 and sigma by under root of n2, because n1 is more than n2. So, this is more, this value will be less. So, the standard error in case of A, in case of this is less, because more number of observations, though the standard deviation is same. What is the meaning of this? The meaning of this is the mean which is associated with this observation set has more precision. We are more confident about that mean than the mean which is coming from here. So, the standard error is a way in which, because in the case of the standard deviation, it does not depend, it does not take into account the number of the observations. Two sets of observations may have same standard deviation, but that's wrong. Standard deviation, yes, it may be same, but when we start talking about the our mean, the value which we are finding from it, our result, then we should not rely upon standard deviation alone. We should talk about standard error, because here we are considering also the number of observations which were taken there in the field and the number of observations which are resulting in this standard deviation. Okay. So, this is important and we should keep this in mind whenever we are reporting, whenever we are judging the observations. Okay. Now, after this, we will start talking about now weighted observations. What is the meaning of this? I will pose one question first. The question is, let us say for a line, there are 5 persons A, B, C and D and E. All they have done the measurements of this line. What they did, they went to the field with a certain tape and they measured this length, maybe on 5 different days, and they come out to the lab with 5 sets of observations. Are all these observations of same reliability? That's the question. Let us say right now also these 5 persons, they go to the field and measure 5 lengths, LA, LB, LC, LD and LE. Now question number 1. Question number 1, will all these LA, LB, LC, LD and LE will be the same or will be the different? Question number 1. Now you should be able to answer this question, because there are 5 individuals who are going to the field with maybe same instrument, but will all these be same? No, they can't be same, because there are many varying factors. The person A, he looks at the instrument in a slightly parallax way. It doesn't look exactly the way the instrument should be read. Person B, maybe he is committing some blunder there. While person C is working, the temperature is more. There is some error in the instrument. Okay, it may be the systematic error. Even if the way you put the instrument there in the ground in order to measure the length, slightly some changes are there. What we saw earlier, we can never measure the true value. Only if we can measure the true value, then only all these observations will be same. So all these observations will have to be different, because the amount of the random error or systematic error which is there in these observations is different. Even if you eliminate your systematic error, still these observations will be different, because the amount of the random error which is there in these observations will be different. Well, so you have got 5 sets of observations, 5 measurements of this length. Now we want to take a mean. Okay, we want to find the mean of this using these 5. Should we straight away sum these sigma L by 5? No, we should not do that. Why we should not do that? Because if we are doing it, we are considering each and every observation to be having the same weight, same reliability. You knew that person A is very sincere, while you also know that person E is not that sincere. You know, when person C was working in the field, the weather was very bad. The working conditions were very, very poor. If that is so, each of these observations will be not equally reliable. They will have different reliability. So this reliability of observation we say as weight, the weight of the observation. An observation which is more reliable is having higher weight, and observation which is having less reliability will have less weight. So along with these observations, what we do, we also make a table. Okay, Now, along with these lengths, we also write WA, WB, WC, WD, WE, and these are the weights of these observations. Well, if our observations are weighted, how can we proceed further? Now, each and every observation is having a different weight. Number one thing, that is how to decide or give weights. How do you want to give the weights? There should be some method. Well, in the methods, number one is by your personal judgment. What is the meaning of that? Well, here we made the personal judgment. I said the person A is very reliable person. He is very sincere. He cannot commit mistake. I gave him higher weight. Person D, oh, he is not that good in working. I give him less weight. Person C, when he was working in the field, the weather conditions were very poor. I give him also less weight. Person B is okay, is all right. So I give him, okay weight. So just like that, the personal judgment. You make a personal judgment and you assign the weights. Can there be some other method? Well, the other method is number of observations. What is the meaning of this? Number of observations. Well, here only, if I extend this table further, now this length was measured by these observers 5 times, 10 times, 20 times, 40 times, 3 times. Okay, we assume, let us say it is given to you that all these observers A, B, C and D are equally sincere and they have done the observations of the same line different number of times. Obviously, this observation has got more weight. This observation having 40 number of observations, because a single thing we have measured 40 number of times, so we can give definitely more weight to that. So the second method of giving these weights is proportional to the number of observations. Can there be any better method? The third one, we give the weights as by the variance, or we can say the precision. We know, for example, now I will draw a diagram here. The same length is being measured now by 2 observers A and B. A has done, for example, let us say 100 measurements. B has also done 100 measurements for this length L. Both of them, A and B, are equally sincere. The weather conditions when they are working in the field are almost same. If that is the case, whom should we give more weight? So what we do, for his 100 measurements and for his 100 measurements, we can find the sigma, and the square of sigma is the variance. Now, why we are giving the weight as per the sigma? What is the reason? Because it gives us the closeness of the observations. An observer who is more sincere, who is working very well, the errors, the sources of the errors in the field are less, the chances are all the observations will be very near to each other, very close to each other. So if the observations are closer, we want to give them more weight. So the weight is given now by variance, inversely proportional to the variance. Less is the variance, okay, less is spread, more is the weight, obviously. So these are the methods by which we can give weights to our observations. Now what we will do, we will look for measures of precision for weighted data or observation. Now, in case of the weighted data, what the weighted data is, you have a length L is measured as L1, L2, L3, Ln. Then you have some weights W1, W2, W3 and Wn to each of these observations. Well, how can you find number one thing, the weighted mean? Weighted mean, because we will need the weighted mean very often whenever we are working with the data. The weighted mean of this observation is sigma Li, where I is 1 to n, divided by, you can guess it very quickly now, that is sigma Wi. That gives you the weighted mean, okay, the weighted arithmetic mean. Now, how about the measure of precision? The measure of precision, number one, we say standard deviation for weighted observation or weighted data. So, the same thing, we just put a little w here in order to indicate that this is the weighted. This is, as we have seen before also, sigma Wi xi minus x bar square. Of course, this xi and x bar are the mean and the observation, okay, and Wi is the weight of the observation divided by n minus 1. So, this gives you the standard deviation of the weighted data. Third, corresponding to the standard error. The standard error, as we had written SE earlier, weighted is divided by I. So, all these are equivalent in terms of their physical meaning to what we have already discussed. We have discussed the standard deviation, what it means, standard error, what it means, where we use it. So, all these measures are also similar to that. So, what we have done, we have discussed about the errors now, the normal distribution, how we make use of that, standard normal curve, how we make use of that. If we are taking the observation, how to report it, what is the meaning of plus minus sigma, okay. Then we saw the precisions, how we can give the precisions. So, this is all what we have discussed in this video lecture. Now, in our next video lecture, again we will continue with the errors in the measurement. So, the fifth lecture of this module will be again in the same. So, we end this lecture today here now. Thank you very much.